Hello, fellow Voyagers, and welcome to the Night Voyager. I'm absolutely delighted you've chosen to join me for a gentle descent into one of science's most astonishing possibilities: wormholes. Mysterious bridges through space-time that blur the line between science fiction and cutting-edge physics. Before we drift into the unknown, I'd be honored if you'd consider subscribing. If these quiet explorations of the universe bring you wonder or calm, you're already one of us, a fellow cosmic dreamer. Now, whether you're winding down for the night, taking a quiet moment for yourself, or simply letting your thoughts wander toward the impossible, you're exactly where you need to be. We're beginning a journey to the edge of known physics, where mathematical equations describe tunnels through space-time that could, at least in theory, allow us to step from one side of the universe to another in an instant. Imagine folding a piece of paper and poking a pencil through both layers. That simple action creates a shortcut between two distant points on the surface. Now imagine doing the same thing with the fabric of space-time itself. What emerges from Einstein's equations isn't just a mathematical curiosity. It is a genuine possibility that the universe might contain tunnels connecting distant regions of space and time. These are no longer just abstract ideas. Recent developments in quantum physics suggest that the strange phenomenon of quantum entanglement, where particles remain mysteriously connected across vast distances, might actually be forming tiny wormhole geometries at the quantum level. The boundary between fiction and reality is softening in ways that would have seemed impossible just a few decades ago. We'll explore how Hollywood fantasies became serious equations, why Einstein himself was surprised by the mathematics, and what modern quantum experiments reveal about traversable wormholes, quantum entanglement, and the shape of space itself. The story of wormholes is really the story of humanity reaching for the boundaries of the possible, using mathematics and imagination to probe the deepest structures of existence. It reminds us that the universe is far stranger, more connected, and more beautiful than it often appears. Long before Einstein's equations suggested that space-time could be folded like origami, human imagination had already dreamed of cosmic shortcuts. Writers envisioned portals and tunnels that could carry travelers across vast distances instantly. What they did not know was that their visions would later align with the most rigorous mathematical physics of the 20th century. The concept of traveling through space via mysterious passages has deep roots in human storytelling. From ancient myths of magical doorways to other realms to Jules Verne's journey to the center of the Earth, we've always been fascinated by the idea of hidden pathways through reality. But it was the golden age of science fiction in the early 20th century that truly crystallized the modern concept of what we now call wormholes. Writers like John Campbell Jr. and later Isaac Asimov began describing space travel through what they called hyperspace, alternate dimensions that allowed starships to bypass the normal constraints of distance and time. These weren't just convenient plot devices, they were sincere attempts to imagine how advanced civilizations might overcome the fundamental problem of cosmic distances. Even traveling at the speed of light, it would take over 4 years to reach the nearest star. For a galaxy-spanning civilization, something more dramatic was needed. The term wormhole itself comes from a beautifully simple analogy, first popularized by physicist John Wheeler in the 1950s. Imagine an apple with a worm tunnel burrowing through it from one side to the other. From the worm's perspective, crawling along the apple's surface represents the long way around, while the tunnel provides a direct shortcut through the interior. Wheeler suggested that space-time might work similarly. What appears to be vast distances on the surface of normal space might be connected by shortcuts tunneling through higher dimensions. But here's where the story becomes truly remarkable. In 1935, decades before Wheeler's popularization of the idea, Albert Einstein and his colleague Nathan Rosen were working through the implications of general relativity when they stumbled upon something unexpected. The equations seemed to describe bridge-like solutions connecting two separate regions of spacetime. These mathematical structures, now known as Einstein-Rosen bridges, weren't science fiction. They emerged naturally from the same equations that accurately describe gravity, planetary orbits, and the bending of light around massive objects. Einstein himself was skeptical. The idea that his equations might allow for cosmic shortcuts seemed too fantastical, too much like imagination rather than physics. That tension between mathematical possibility and physical plausibility would become a defining feature of wormhole research for decades. The cultural impact of the wormhole concept grew throughout the mid-20th century, especially as space exploration became a reality and the vastness of space became undeniable. When the Apollo missions sent humans to the moon, a journey of just 240,000 miles that took 3 days, it highlighted just how enormous space truly is. The nearest star is more than 100 million times farther than the moon. Even with perfect technology approaching the speed of light, interstellar travel seemed to require either generational ships or some kind of shortcut through spacetime itself. Science fiction writers embraced this challenge with increasing sophistication. Authors like Ursula K. Le Guin, in her novel The Dispossessed, began exploring not just the mechanics of faster-than-light travel, but its philosophical and emotional implications. If you could step through a portal and instantly arrive at a distant world, what would that mean for concepts of home, journey, and the meaning of distance itself? Television and film further embedded wormhole concepts into popular culture. The original Star Trek series introduced the idea of stable, artificial wormholes that could be used for regular transportation. Later, shows like Stargate and Star Trek Deep Space Nine made wormholes central to their storylines, depicting them as both gateways to adventure and sources of cosmic mystery and danger. What's fascinating is how these fictional portrayals often anticipated real scientific developments. Long before physicists understood the role of exotic matter in stabilizing wormholes, science fiction writers were already imagining the technological challenges of keeping cosmic tunnels open and safe for travel. They intuited that such shortcuts would require unprecedented mastery over the fundamental forces of nature. But perhaps no science fiction franchise has shaped our modern visualization of wormholes quite like Stargate. When the original 1994 film introduced audiences to the concept of stepping through a shimmering portal and instantly arriving on distant worlds, it crystallized an image that would define how millions of people think about cosmic travel. The Stargate concept was elegant in its simplicity. A ring-shaped device that could establish stable wormhole connections to specific destinations across the galaxy. What made Stargate particularly compelling from a scientific perspective was its attempt to ground fantastic concepts in plausible physics. The show introduced ideas like point-of-origin coordinates, energy requirements for maintaining wormhole connections, and even the dangers of unstable vortexes. The visual representation became iconic. That rippling, water-like event horizon that characters could step through, the way matter would be deconstructed and transmitted through subspace. The concept that you could literally walk from one world to another as easily as stepping through a doorway. For many viewers, this became the definitive image of what wormhole travel should look like. Stargate also explored concepts that theoretical physicists would later investigate seriously. The idea that wormholes could connect not just distant locations but different points in time. The notion that advanced civilizations might build networks of these cosmic shortcuts, creating galactic civilizations connected by instantaneous travel. Even the concept that such technology might be so advanced as to appear magical to less developed species. The franchise's influence extended beyond entertainment. It inspired a generation of physicists and engineers who grew up watching characters step through those shimmering portals. Some of today's researchers working on theoretical wormhole physics cite Stargate as an early inspiration, a way of visualizing concepts that pure mathematics alone couldn't capture. What's remarkable is how Stargate's portrayal of wormhole travel anticipated many of the questions that real physicists would later grapple with. What would it feel like to have your atoms disassembled and reassembled? Would consciousness survive such a journey? How would you maintain stable connections across cosmic distances? The show explored these ideas through narrative, creating a cultural framework for understanding concepts that were still purely theoretical. The Stargate universe also introduced the idea that wormholes might be engineered rather than naturally occurring. Long before physicists seriously considered the possibility of artificial wormhole construction, the franchise was exploring what such technology might look like and how advanced civilizations might use it. In this sense, science fiction was once again serving as a form of theoretical exploration, testing ideas that mathematics would later investigate. This progression from science fiction speculation to serious scientific inquiry reflects something profound about how human imagination and rigorous research can work together. The dreams of writers and filmmakers weren't just entertainment, they were expanding our conceptual vocabulary, giving us new ways to think about space, time, and the possibilities hidden within the laws of physics. When Albert Einstein first derived his field equations of general relativity in 1915, he was attempting to describe something seemingly straightforward: how mass and energy curve the fabric of spacetime to create what we experience as gravity. What he didn't expect was that these equations would predict phenomena so bizarre they challenged the very foundations of our understanding of reality. Among the strangest of these predictions were solutions that seemed to describe bridges or tunnels connecting distant regions of spacetime, what we now call Einstein-Rosen bridges. The mathematical journey to discovering these cosmic shortcuts begins with understanding how Einstein revolutionized our concept of space and time. Before relativity, we imagined space as a fixed, unchanging stage upon which the drama of physics played out. Time was universal, flowing at the same rate everywhere in the universe. Gravity was simply a force that pulled objects together across empty space. Einstein's breakthrough was recognizing that space and time are not separate, fixed entities, but aspects of a single dynamic fabric called spacetime. This fabric can be curved, stretched, and warped by the presence of mass and energy. What we experience as gravity is actually the result of objects following the straightest possible paths through this curved spacetime geometry. Imagine placing a bowling ball in the center of a stretched rubber sheet. The ball creates a depression in the sheet's surface. Now roll a marble nearby. It will naturally curve toward the bowling ball, not because of some mysterious force reaching across empty space, but because it's following the curved geometry created by the ball's presence. This is essentially how gravity works according to general relativity, except instead of a two-dimensional sheet, we're dealing with the four-dimensional fabric of spacetime itself. Einstein's field equations describe exactly how matter and energy curve this spacetime fabric, but equations once written down often contain solutions that their creators never anticipated. In 1935, Einstein was working with his colleague Nathan Rosen to understand what happens to spacetime geometry around extremely dense objects like black holes. They were trying to resolve what seemed like mathematical pathologies, points where the equations appeared to predict infinite curvature and other impossible conditions. What Einstein and Rosen discovered was that the equations naturally described solutions where spacetime curves so dramatically that it effectively folds back on itself, creating a bridge or tunnel connecting two separate regions. Picture taking that rubber sheet analogy and imagining it curving so extremely that it touches itself, creating a tube or tunnel through which you could theoretically travel from one region to another without crossing the intervening space. These mathematical bridges exist in what physicists call the maximally extended solution to Einstein's equations. When you solve the equations completely, without making simplifying assumptions, the geometry that emerges naturally includes these connecting tunnels. It's as if the mathematics itself was insisting that cosmic shortcuts were not just possible, but inevitable consequences of the way spacetime responds to extreme curvature. However, Einstein and Rosen quickly realized that these bridges came with a devastating problem. They were fundamentally unstable. The moment anything, even a single photon of light, attempted to travel through the wormhole, the bridge would collapse catastrophically fast. The tunnel would pinch off before the light could complete its journey, effectively sealing both ends and trapping anything inside in a region of infinitely curved spacetime. The mathematics revealed that keeping a wormhole open would require something that seemed physically impossible: matter with negative energy density. This so-called exotic matter would need to have gravitational properties exactly opposite to normal matter. Instead of attracting other matter, it would repel it. Instead of warping space-time in the familiar way that creates gravity wells, it would create gravity hills that push things away. This requirement for exotic matter appeared to make traversable wormholes permanently impossible. Normal matter and energy always have positive mass and energy density. It's one of the fundamental assumptions underlying all of physics. The idea that exotic matter with negative energy density could exist seemed to violate basic principles like the conservation of energy. But the story of wormhole physics is full of unexpected turns. In the 1970s and 1980s, advances in quantum field theory began revealing that the vacuum of space is far more complex and dynamic than previously imagined. Quantum mechanics tells us that apparently empty space is actually filled with virtual particle pairs constantly popping into existence and annihilating each other. These quantum fluctuations create what's called the zero-point energy of the vacuum. More intriguingly, physicists discovered that under certain circumstances it's possible to create regions where the energy density is actually lower than the normal vacuum state. This creates pockets of what's effectively negative energy density, exactly the exotic matter that Einstein-Rosen bridges require to remain stable and traversable. The most famous example of this effect is the Casimir force, first predicted by Dutch physicist Hendrik Casimir in 1948. When two parallel metal plates are placed very close together in a vacuum, quantum effects cause them to experience an attractive force. This happens because the quantum vacuum between the plates contains less energy than the vacuum outside, effectively creating a region of negative energy density. The Casimir effect has been measured experimentally with extraordinary precision, confirming that negative energy states are not just theoretical possibilities but observable features of reality. This discovery transformed wormhole physics from pure mathematical speculation into a field with genuine experimental foundations. Modern calculations suggest that creating a human traversable wormhole would require exotic matter roughly equivalent to the mass energy of Jupiter, but with negative energy density. The engineering challenges are staggering. We're talking about manipulating matter and energy on scales that dwarf anything in human experience. Yet the fundamental physics doesn't rule it out entirely. Recent theoretical work has also revealed that wormhole geometries might emerge naturally under certain extreme conditions. Some cosmologists speculate that the Big Bang itself might have created a network of microscopic wormholes that could theoretically be expanded and stabilized by sufficiently advanced technology. Others suggest that the interiors of black holes might naturally produce wormhole connections to distant regions of space-time, or even other universes entirely. The mathematics of Einstein-Rosen bridges also reveals deep connections to some of the most fundamental questions in physics. The geometry of a wormhole is intimately related to the information paradox surrounding black holes, the nature of quantum entanglement, and even questions about consciousness and the flow of time. Perhaps most remarkably, the same equations that predict mundane phenomena like planetary orbits and GPS satellite corrections also naturally describe these cosmic shortcuts that could theoretically allow near-instantaneous travel across the universe. This suggests something profound about the mathematical structure underlying reality, that space and time are far more flexible and interconnected than our everyday experience suggests. Einstein himself remained skeptical of wormholes throughout his lifetime, viewing them as mathematical curiosities rather than physical possibilities. He famously referred to them as Spukkraftfernwirkung, spooky action at a distance, similar to his concerns about quantum entanglement. Yet both phenomena have since proven to be fundamental features of the universe, suggesting that Einstein's equations were wiser than even their creator initially realized. In the summer of 2022, physicists at Harvard and MIT achieved something that would have seemed like pure science fiction just decades earlier. They created a quantum wormhole in a laboratory. Using a quantum computer with just 9 quantum bits, they simulated the teleportation of information through a bridge in space-time. While this wasn't a traversable wormhole in the traditional sense, it represented a breakthrough in our understanding of one of the most profound connections in modern physics. The relationship between quantum entanglement and the geometry of space-time itself. This connection is captured in what physicists call the ER equals EPR conjecture, one of the most elegant and mind-bending ideas to emerge from theoretical physics in recent decades. The name refers to 2 famous papers from the 1930s, the Einstein-Rosen paper that predicted wormhole bridges, and the Einstein-Podolsky-Rosen paper that highlighted the strange phenomenon of quantum entanglement. The conjecture suggests these 2 seemingly unrelated phenomena might actually be different descriptions of the same underlying reality. To understand this connection, we need to dive into the bizarre world of quantum entanglement. When 2 particles become entangled, they form a unified quantum system where measuring one particle instantly affects the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance because it seemed to violate the principle that nothing can travel faster than light, including information. Imagine 2 coins that have been quantum entangled. No matter how far apart you take them, across the room, across the galaxy, across the universe, flipping one coin to heads will instantly force the other to land on tails. The correlation is perfect and instantaneous, as if the coins remain connected by some invisible thread that transcends space and time. For decades, physicists viewed this as a curious feature of quantum mechanics that had no relation to gravity or space-time geometry. Entanglement was the domain of particle physics and quantum information theory, while gravity and space-time curvature belonged to cosmology and general relativity. These were separate realms of physics that happened to coexist in the same universe. But in 2013, physicists Juan Maldacena and Leonard Susskind proposed something revolutionary. What if quantum entanglement and wormhole bridges are actually the same phenomenon viewed from different perspectives? What if every pair of entangled particles is connected by a microscopic wormhole threading through the fabric of space-time? This idea emerges from some of the most advanced theoretical physics of the past few decades, particularly the holographic principle and string theory. These frameworks suggest that the information content of any region of space can be encoded on its boundary, much like how a hologram encodes 3-dimensional information on a 2-dimensional surface. In this view, what we perceive as the interior volume of space might actually be an emergent property of quantum entanglements between points on the boundary. Mathematics becomes truly elegant when you realize that Einstein's equations and the equations of quantum mechanics are describing the same geometric relationships from different angles. When particles become entangled, they're not just sharing quantum information, they're creating a bridge through space-time that connects their locations. The stronger the entanglement, the more robust the wormhole connection. This relationship helps resolve some of the deepest puzzles in physics. For instance, the information paradox of black holes. The question of what happens to information that falls into a black hole might be solved if entangled particles straddling the event horizon are connected by tiny wormholes. Information that appears to be lost forever might actually be preserved in the quantum geometry of space-time itself. The 2022 laboratory experiment that created a quantum wormhole worked by establishing maximum entanglement between quantum bits on opposite sides of a quantum computer, then demonstrating that information could be teleported through this quantum bridge. While the wormhole existed only in the abstract space of quantum information rather than physical spacetime, the experiment confirmed that the mathematical structure of wormholes and entanglement are indeed closely related. But the implications go far beyond laboratory curiosities. If ER equals EPR is correct, then the fabric of spacetime itself might be woven from quantum entanglement. Every cubic centimeter of seemingly empty space could be threaded with microscopic wormholes connecting distant regions of the universe. These quantum bridges would normally be far too small and short-lived to allow travel, but they might form the fundamental substrate from which the larger-scale structure of spacetime emerges. This perspective transforms our understanding of what a wormhole actually is. Instead of thinking of them as exotic tunnels carved through space, we might think of them as the natural expression of quantum correlations between distant regions. In this view, traversable wormholes wouldn't require exotic matter to hold them open. They would be stabilized by the same quantum entanglement that maintains the coherence of spacetime itself. Recent theoretical work has explored how this connection might work in practice. Some physicists propose that sufficiently advanced civilizations could amplify naturally occurring quantum entanglements to create macroscopic wormholes. By carefully manipulating the quantum fields that permeate space, it might be possible to strengthen the microscopic bridges that already exist and expand them to sizes that could allow matter to pass through. This approach sidesteps some of the traditional problems with wormhole physics. Instead of needing exotic matter with negative energy density, you would need quantum technologies capable of precisely controlling entanglement across vast distances. While still enormously challenging, this seems more physically plausible than creating Jupiter-mass quantities of negative energy. The quantum perspective also offers new insights into what wormhole travel might actually feel like. If you were to travel through a quantum wormhole, you wouldn't be moving through a tunnel in the conventional sense. Instead, your quantum state would become entangled with the space-time geometry connecting two distant regions. From your perspective, you might experience a kind of quantum teleportation, where your information pattern is deconstructed at one end and reconstructed at the other. This raises profound questions about consciousness and personal identity. If your thoughts, memories, and personality are encoded in the quantum states of your brain, and if those states are teleported through a wormhole while your physical matter is left behind, would the reconstructed being at the other end still be you, or would it be a perfect copy with no continuity of consciousness? The ER equals EPR conjecture also suggests that the universe might be far more interconnected than we realize. Every quantum entanglement, from the subatomic particles in your body to the cosmic ray interactions in distant galaxies, could be creating tiny threads in the fabric of space-time. The universe might be held together not just by gravity and electromagnetic forces, but by a vast network of quantum bridges threading through every corner of existence. Perhaps most remarkably, this connection between entanglement and geometry might provide clues about the ultimate nature of reality. If space-time itself emerges from quantum entanglement, then space and time might not be fundamental features of the universe, but emergent properties of more basic quantum information relationships. In this view, the universe would be less like a stage upon which quantum events occur, and more like a vast quantum computer processing information through an intricate network of wormhole connections. As our understanding of quantum entanglement and space-time geometry continues to evolve, the boundary between science fiction and science continues to blur. What began as Einstein's mathematical curiosity has become a window into the deepest structures of reality, suggesting that the universe might be stranger, more connected, and more amenable to transformation than we ever dared imagine. The quantum revolution is revealing that space and time themselves might be illusions, with the true reality being the patterns of entanglement that weave the cosmos together. While theoretical physicists explore the mathematical possibilities of wormholes, observational astronomers face a more practical question: do these cosmic shortcuts actually exist in nature? The search for natural wormholes has become one of the most intriguing challenges in modern astrophysics, requiring creative thinking about what signatures these invisible bridges might leave behind, and where in the universe they might be hiding. The fundamental challenge in hunting for wormholes is that they would be, by their very nature, nearly invisible. Unlike stars, galaxies, or black holes which emit or absorb light in characteristic ways, a stable wormhole would be essentially transparent. Light entering one mouth of the wormhole would simply emerge from the other mouth, potentially in a completely different part of the universe. From our perspective, we might see distant stars and galaxies through the wormhole opening, but we wouldn't see the wormhole itself. However, the gravitational effects of wormholes would be detectable. Just like black holes, wormhole mouths would have significant mass and would bend spacetime around them. This curvature would act as a gravitational lens, distorting and magnifying the light from objects positioned behind the wormhole from our perspective. But here's where the detective work becomes subtle, distinguishing between gravitational lensing caused by a wormhole and lensing caused by more conventional objects like galaxy clusters or black holes. The key difference lies in the details of how light bends around these objects. A black hole creates what physicists call a photon sphere, a region where light can orbit the black hole at a specific distance. This creates characteristic features in gravitational lensing that act like cosmic fingerprints. Wormholes, by contrast, would create different lensing patterns because their geometry is fundamentally different. Instead of having a central singularity surrounded by curved space, a wormhole has a throat connecting two separate regions of space-time. Some astronomers have proposed looking for what they call achromatic gravitational lensing. This would appear as magnification of background objects that doesn't depend on the wavelength of light, a signature that might distinguish wormhole lensing from other phenomena. Others have suggested searching for time delays in variable sources seen through gravitational lenses. If you're observing a pulsar or variable star through a wormhole, the light taking different paths through the curved space-time around the wormhole mouth would arrive at Earth at slightly different times, creating a characteristic signature. One of the most promising search strategies focuses on the centers of galaxies. Many galaxies, including our own Milky Way, harbor supermassive black holes at their centers. But what if some of these apparent black holes are actually wormhole mouths? The gravitational effects would be similar enough that we might have been mistaking wormholes for black holes all along. The difference would show up in how matter behaves near the object's surface. When material falls into a black hole, it heats up and emits intense radiation as it approaches the event horizon before disappearing forever. But material falling into a wormhole mouth would simply pass through to the other side. This might create subtle differences in the accretion disk patterns and radiation signatures that careful observation could detect. Recent advances in gravitational wave astronomy have opened entirely new possibilities for wormhole detection. When massive objects accelerate through curved space-time, they create ripples in the fabric of space and time that propagate outward at the speed of light. The LIGO and Virgo detectors have already observed gravitational waves from colliding black holes and neutron stars. But what would gravitational waves from wormhole interactions look like? Some theoretical models suggest that if two wormhole mouths were to collide or merge, they would create gravitational wave signatures distinctly different from black hole mergers. The waves might have characteristic frequency patterns or polarizations that would reveal the exotic nature of the colliding objects. As gravitational wave detectors become more sensitive, they might catch these cosmic events and provide the first direct evidence of natural wormholes. Another intriguing possibility involves primordial wormholes, cosmic shortcuts that might have formed during the earliest moments of the universe. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion called cosmic inflation. The extreme conditions during this epoch might have created quantum fluctuations large enough to form stable wormhole connections between different regions of the expanding space-time. These primordial wormholes would be ancient, nearly as old as the universe itself. Over billions of years they might have evolved in complex ways. Some could have grown larger by accreting matter and energy. Others might have formed networks, creating a cosmic subway system connecting distant parts of the universe. The mouths of these ancient wormholes might now appear as unusual gravitational objects whose properties don't quite match any known type of astronomical body. Cosmologists have also speculated about the role wormholes might play in cosmic structure formation. The web-like pattern of galaxies and galaxy clusters we observe today grew from tiny density fluctuations in the early universe. But what if some of these structures were shaped by wormhole connections? A network of cosmic shortcuts could have influenced how matter flowed and accumulated over cosmic time, potentially leaving detectable signatures in the large-scale distribution of galaxies. The search for natural wormholes has also led astronomers to look more carefully at some of the universe's most extreme environments. The cores of active galactic nuclei, where supermassive black holes are thought to power jets of particles at near-light speeds, might actually be powered by matter flowing through wormhole connections to distant regions of space. Some gamma-ray bursts, the most energetic explosions known in the universe, might be caused by matter suddenly emerging from wormhole mouths rather than traditional stellar collapse. Perhaps most intriguingly, some researchers have suggested that dark matter, the mysterious substance that makes up most of the matter in the universe but doesn't interact with light, might be connected to wormhole physics. What if dark matter particles are actually ordinary matter that exists on the other side of microscopic wormhole connections? This could explain why we can detect dark matter's gravitational effects but never see it directly. It's literally in another part of space-time, connected to our region only through quantum-scale wormhole bridges. Recent observational campaigns have begun systematically searching for wormhole signatures. Projects like the Event Horizon Telescope, which captured the first image of a black hole's shadow, are also perfectly positioned to detect the characteristic signatures of wormhole mouths. Future space-based telescopes with unprecedented sensitivity and resolution might be able to spot the subtle gravitational lensing effects or radiation patterns that would reveal natural wormholes. The hunt for natural wormholes represents more than just an exotic astronomical search. It's a test of our understanding of the fundamental nature of space-time. If wormholes exist naturally, it would confirm that the universe is far more interconnected and dynamic than conventional models suggest. What makes this search particularly compelling is that even a negative result would be scientifically profound. If systematic surveys fail to find any evidence of natural wormholes, it would place important constraints on the physics of exotic matter, the topology of space-time, and the conditions that existed during the early universe. Sometimes in science, learning what doesn't exist is just as valuable as discovering what does. The challenge of detecting something that might be invisible reminds us that the universe could be filled with phenomena that remain hidden simply because we don't yet know how to look for them. Every major astronomical discovery, from pulsars to black holes to gravitational waves, required developing new observational techniques and learning to recognize signatures that had never been seen before. Wormholes might be the next addition to this cosmic bestiary, waiting patiently for the right combination of theoretical insight and observational ingenuity to reveal their presence. If natural wormholes remain elusive, could sufficiently advanced civilizations create their own cosmic shortcuts? The prospect of engineering traversable wormholes represents perhaps the ultimate expression of technological mastery. The ability to reshape space-time itself according to conscious design. While the challenges are staggering, recent advances in our understanding of exotic matter, quantum fields, and space-time geometry suggest that artificial wormholes might not be forever beyond the reach of intelligence. The fundamental requirement for any traversable wormhole is exotic matter with negative energy density. This isn't just unusual matter. It's matter that behaves in ways that seem to violate our basic intuitions about how the universe works. Normal matter and energy always have positive mass and positive energy density. They create gravitational attraction, pulling other matter toward them and warping space-time in the familiar way that creates gravity wells around planets and stars. Exotic matter would do exactly the opposite. It would have negative energy density and would create gravitational repulsion, pushing other matter away and warping space-time into what physicists call gravity hills rather than gravity wells. This anti-gravitational effect is precisely what's needed to hold open the throat of a wormhole against the natural tendency of curved space-time to collapse the tunnel. For decades, the requirement for exotic matter seemed to make traversable wormholes physically impossible. The very idea of negative energy density appeared to violate fundamental principles like the weak energy condition, which states that energy density should always be positive in any reasonable physical theory. Creating exotic matter seemed as impossible as creating perpetual motion machines or faster-than-light communication. But quantum field theory has revealed that the universe is far more subtle and flexible than classical physics suggested. The quantum vacuum, what we think of as empty space, is actually teeming with virtual particle pairs that constantly pop into existence and annihilate each other in tiny fractions of a second. These quantum fluctuations give the vacuum a baseline energy density, but under certain circumstances, it's possible to create regions where the local energy density is actually lower than this vacuum state. The Casimir effect provides the clearest example of this phenomenon. When two parallel conducting plates are placed very close together in a vacuum, quantum effects cause them to experience an attractive force. This happens because the quantum vacuum between the plates has lower energy density than the vacuum outside, effectively creating a region of negative energy density relative to the normal vacuum state. Building on this foundation, physicists have proposed various mechanisms for creating and concentrating exotic matter in quantities sufficient for wormhole construction. One approach involves using intense electromagnetic fields to squeeze the quantum vacuum, creating regions of negative energy density. Another involves manipulating the topology of space itself, using techniques borrowed from proposed experiments in laboratory cosmology. The engineering challenges are nonetheless staggering. Current calculations suggest that creating a human traversable wormhole would require exotic matter equivalent to the mass energy of Jupiter, but with negative energy density. We're talking about manipulating matter and energy on scales that dwarf anything in human experience. The total energy budget of human civilization is minuscule compared to what would be needed for wormhole engineering. However, the energy requirements might be dramatically reduced if certain theoretical predictions prove correct. Some models suggest that microscopic wormholes, too small for human travel but large enough for information transmission, might require exotic matter equivalent to only a few elementary particles. Advanced quantum technologies might be able to create and manipulate such tiny cosmic shortcuts, potentially enabling faster-than-light communication even if faster-than-light travel remains impossible. The construction process itself would require unprecedented mastery over the fundamental forces of nature. Engineers would need to precisely control gravitational fields, manipulate quantum vacuum states, and coordinate matter and energy flows across potentially vast distances. The wormhole mouth locations would need to be chosen carefully, with consideration for gravitational stability, cosmic radiation environments, and the long-term evolution of their stellar neighborhoods. One proposed construction method involves starting with naturally occurring quantum-scale wormholes and gradually expanding them using controlled infusions of exotic matter. The expansion process would need to be extraordinarily precise. Too little exotic matter, and the wormhole would collapse. Too much and it might become unstable in unpredictable ways. The engineering tolerances would make rocket science look like kindergarten crafts. Safety considerations for wormhole construction raise equally daunting challenges. A traversable wormhole would essentially be a permanent alteration to the local structure of spacetime. Any mistakes in its creation or maintenance could have consequences ranging from localized spacetime distortions to potentially universe-threatening causality violations. The engineering team would need to understand not just how to build a wormhole, but how to contain and control its effects on the surrounding cosmos. The social and economic implications of wormhole technology would be equally transformative. Instant transportation between arbitrary points in space would fundamentally alter concepts of distance, territory, and national boundaries. The civilization that first develops traversable wormholes would gain an overwhelming strategic advantage, able to project power and influence across cosmic distances instantaneously. Recent theoretical work has explored whether more modest wormhole technologies might be achievable with less exotic requirements. Some physicists have proposed semi-classical wormholes that use conventional matter arranged in unusual configurations, possibly requiring only precise control over electromagnetic fields rather than exotic matter with negative energy density. Others have investigated whether wormholes might be stabilized using quantum entanglement effects rather than exotic matter. Building on the ER equals EPR connection we explored earlier, the development of wormhole engineering would likely parallel the development of other advanced spacetime technologies. Civilizations working toward wormhole construction would probably also develop capabilities for gravitational wave generation and detection, precise manipulation of spacetime curvature, and perhaps even controlled creation of closed time-like curves for limited time travel applications. From our current perspective, wormhole engineering seems impossibly advanced, requiring mastery over physical phenomena. We're only beginning to understand an energy resources far beyond anything our civilization has ever contemplated. Yet the history of technology is filled with achievements that once seemed equally impossible. Powered flight, space travel, nuclear energy, quantum computers, all were once purely theoretical concepts that seemed to violate basic assumptions about what was possible. What makes wormhole engineering particularly intriguing is that it doesn't appear to violate any fundamental laws of physics. The exotic matter requirements are extreme but not impossible. The energy scales are vast but not infinite. The engineering challenges are unprecedented but not necessarily insurmountable for a sufficiently advanced technological civilization. Perhaps most remarkably, wormhole engineering represents the ultimate expression of intelligence triumphing over the apparent limitations of physical reality. By understanding the deep mathematical structures underlying space-time, a sufficiently advanced civilization could literally reshape the universe to overcome the tyranny of distance and time. They could transform the cosmos from a hostile void separating distant islands of matter into a connected network where every point is potentially adjacent to every other point. The prospect of engineering cosmic shortcuts reminds us that the boundary between possible and impossible is often determined more by the limits of our current understanding than by absolute constraints built into the fabric of reality. What seems like science fiction today might be the mundane technology of tomorrow, applied by civilizations that have learned to treat spacetime itself as raw material for conscious design. What would it actually feel like to step through a wormhole? This question sits at the intersection of rigorous physics and profound human curiosity, forcing us to imagine experiences that have no analogue in our earthbound existence. The journey through folded spacetime would challenge not just our understanding of physics, but our fundamental concepts of motion, causality, and the nature of existence itself. From the outside, approaching a wormhole mouth would initially seem almost anticlimactic. Unlike the dramatic event horizon of a black hole, where space and time become severely distorted and tidal forces threaten to tear apart anything that ventures too close, a properly constructed wormhole would appear surprisingly benign. The mouth might look like a spherical region where the star field behind it appears distorted, similar to looking through a glass lens that bends and magnifies distant objects. But this calm exterior would conceal one of the most profound alterations to spacetime geometry possible within the known laws of physics. As you approach the wormhole mouth, you would gradually enter a region where the normal relationships between space and time break down in extraordinary ways. The throat of the wormhole represents a place where distant regions of space-time are directly connected, where the concepts of here and there lose their conventional meaning. The experience of crossing the threshold would depend critically on the specific geometry and size of the wormhole. A microscopic wormhole, barely larger than a proton, would require some form of quantum teleportation or information transfer, rather than physical transit. Your consciousness and memories might be encoded as quantum information, transmitted through the wormhole, and reconstructed on the other side, raising profound questions about whether the reconstructed being would still be you or merely a perfect copy. A macroscopic wormhole large enough for human travel would offer a very different experience. As you approach the throat, you might notice that light and radio signals begin behaving strangely. Communications with people outside the wormhole could become delayed or distorted as electromagnetic waves follow the curved spacetime geometry. Your view of the universe behind you would begin to shift and distort as the wormhole's gravitational field acts as a lens, bending light from distant stars and galaxies. The moment of crossing into the wormhole throat itself would be unlike anything in human experience. You wouldn't be traveling through a tunnel in any conventional sense. Instead, you would be moving through a region where the topology of space itself has been fundamentally altered. The throat represents a bridge between distant regions of space-time, and traversing it would mean temporarily existing in a place that is simultaneously here and there according to the normal geometry of the universe. Time would behave in particularly strange ways during the transit, depending on the wormhole's construction and the relative motion of its two mouths. You might experience time dilation effects that cause time to pass differently for you compared to observers outside the wormhole. If one mouth of the wormhole is moving at high speed relative to the other, you could potentially emerge from the wormhole at a different time than when you entered, effectively traveling into your own past or future. The possibility of time travel through wormholes raises some of the most mind-bending paradoxes in physics. If you could travel backward in time and alter past events, you might create causal loops that violate our basic understanding of cause and effect. The famous grandfather paradox asks what would happen if you traveled back in time and prevented your own birth. Would you create an alternate timeline? Would the universe somehow prevent the paradox from occurring? Or would reality itself be torn apart by irreconcilable contradictions? Physicists have proposed various solutions to these temporal paradoxes. The Novikov self-consistency principle suggests that the universe would somehow conspire to prevent paradox-creating events from occurring. Any attempt to change the past would fail in ways that preserve the consistency of the timeline. Other theories propose that time travel would create branching timelines or parallel universes, allowing paradoxes to be resolved through infinite multiplication of realities. The physical sensations of wormhole travel would depend on factors we can only guess at. If the wormhole throat is short enough, the journey might be instantaneous from your perspective. One moment you're entering the mouth in one part of the universe, the next moment you're emerging in a completely different location. Longer wormhole throats might allow you to experience the transition more gradually, perhaps seeing the strange geometries of folded space-time surrounding you as you travel. The exotic matter required to hold the wormhole open might also affect your experience. Negative energy density could create unusual gravitational effects during transit, potentially causing sensations of weightlessness, altered acceleration, or even gravitational forces pointing in impossible directions. Your body's biological processes might respond unpredictably to exposure to exotic matter and the extreme space-time curvatures within the wormhole throat. Emerging from the other side of the wormhole would bring its own set of extraordinary experiences. Depending on where the exit mouth is located, you might find yourself in a completely different galaxy, billions of light years from Earth. The star patterns would be utterly unfamiliar, the constellations bearing no resemblance to anything in Earth's night sky. If the wormhole connected to a parallel universe with different physical laws, the very nature of matter and energy might behave differently than anything in your experience. The psychological impact of such travel would be profound. Human consciousness evolved to navigate three-dimensional space and linear time within the confines of a single planet. The experience of instantaneously traversing cosmic distances or stepping outside the normal flow of causality would challenge the fundamental categories through which we understand reality. Some philosophers have speculated that wormhole travel might require new forms of consciousness or cognitive enhancement, simply to process experiences that have no precedent in terrestrial life. The return journey would add another layer of complexity. If the wormhole's mouths have moved relative to each other during your absence, you might return to an Earth that exists at a different time than when you left. Relativistic effects could cause you to age differently than people who remained behind, creating temporal displacement even without explicit time travel. Perhaps most intriguingly, regular wormhole travel might fundamentally alter human concepts of identity, location, and belonging. If you could step from Earth to distant galaxies as easily as walking from one room to another, what would concepts like home or nationality mean? How would human society adapt to the possibility of instantaneous travel across arbitrary distances? Would we remain a single species, or would isolated populations in distant parts of the universe gradually evolve into something no longer recognizably human? The democratization of wormhole travel would likely create the ultimate nomadic civilization, where physical distance becomes meaningless, and the entire observable universe becomes humanity's neighborhood. We might develop new forms of art, literature, and philosophy inspired by experiences that transcend the normal limitations of space and time. Music might incorporate harmonies from gravitational waves, painting might capture the visual experience of folded space-time, and poetry might explore the emotional landscape of existing simultaneously in multiple locations. Yet for all these speculative possibilities, the actual experience of wormhole travel remains tantalizingly beyond our current understanding. We can calculate the mathematics of space-time geometry and exotic matter, but we cannot truly imagine what consciousness would feel like when it encounters realities that have no precedent in evolutionary history. The journey through folded space would be humanity's first step into a larger universe, where the impossible becomes routine, and the boundaries of physical law become raw material for conscious exploration. In this sense, wormhole travel represents more than just advanced transportation. It embodies the ultimate expression of intelligence transcending the apparent limitations of physical reality. By understanding the deep structures of space-time and learning to manipulate them according to conscious design, a civilization could transform the universe from a collection of isolated islands separated by impossible distances into a unified realm, where every point is connected to every other point, where thought and matter can traverse cosmic distances as easily as stepping through a doorway. As we reach the final stage of our journey through the mathematics and possibilities of wormholes, we arrive at questions that transcend physics and touch the deepest mysteries of existence itself. Wormholes are more than just theoretical shortcuts through space-time. They represent windows into the fundamental nature of reality, consciousness, and the strange relationship between mind and cosmos that allows the universe to understand itself. The very fact that wormholes emerge naturally from Einstein's equations tells us something profound about the mathematical structure underlying reality. When physicists write down equations to describe gravity, space-time, and the behavior of matter and energy, those equations don't just predict planets orbiting stars or light bending around massive objects. They also naturally describe bridges connecting distant regions of space-time, pathways that could theoretically allow matter, energy, and information to traverse cosmic distances instantaneously. This suggests that the universe is far more interconnected than our everyday experience indicates. We navigate a world where cause precedes effect, where here and there are absolutely distinct, and where the shortest distance between 2 points is always a straight line. But the deeper mathematical reality revealed by general relativity describes a cosmos where space and time are malleable, where distant regions can be directly connected, and where the familiar rules of causality might be more flexible than we imagine. The connection between wormholes and quantum entanglement adds another layer to this mystery. If the ER equals EPR conjecture is correct, then every quantum entanglement creates a microscopic bridge through space-time. The particles in your body, the atoms in the air around you, the photons streaming from distant stars, all of them are constantly creating and maintaining tiny wormhole connections that thread through the fabric of space and time. This would mean that reality is far more interwoven than it appears. The universe wouldn't be a collection of separate objects isolated in empty space, but rather a vast network of quantum bridges connecting every particle to every other particle across arbitrary distances. In this view, the apparent separateness of objects and events would be an illusion created by our limited perspective. At the deepest level, everything would be intimately connected to everything else through an invisible web of space-time geometry. These connections raise profound questions about the nature of consciousness and its relationship to physical reality. If your thoughts and memories are encoded in the quantum states of neurons in your brain, and if those quantum states are connected to the rest of the universe through microscopic wormhole bridges, then consciousness might not be localized to your brain in the way we typically imagine. Your mind might be distributed across space-time through quantum entanglement, connected to distant regions of the cosmos in ways that transcend ordinary space and time. This perspective offers new ways of thinking about some of the deepest problems in philosophy and science. The hard problem of consciousness, how subjective experience arises from objective physical processes, might be resolved if consciousness is not generated by the brain but rather accessed through quantum connections to a more fundamental level of reality. The mind-body problem might dissolve if mind and body are different aspects of the same underlying quantum geometry. The possibility of traversable wormholes also forces us to confront fundamental questions about the nature of identity and continuity of experience. If you could travel through a wormhole to a distant part of the universe, or if your quantum information could be transmitted through a microscopic wormhole and reconstructed elsewhere, would the person who emerges on the other side still be you, or would they be a copy with your memories but no continuity of consciousness? These questions become even more complex when we consider the possibility of wormholes connecting not just distant regions of space, but different points in time or even parallel universes. If you could travel backward through time and meet your younger self, which version would be the real you? If wormholes connect to universes where different versions of history unfolded, how many copies of yourself might exist across the multiverse? The engineering of artificial wormholes would represent the ultimate expression of intelligence triumphing over the apparent limitations of physical law. A civilization capable of reshaping space-time according to conscious design would have achieved something unprecedented in cosmic history: the ability to transform the fundamental structure of reality itself. They would no longer be bound by the constraints of distance, time, or even causality. They could travel not just through space but through possibility itself. Such capabilities would transform the meaning of existence in ways we can barely imagine. Death might become optional if consciousness could be preserved and transmitted through quantum wormhole networks. The boundaries between individual minds might dissolve if thoughts and memories could be shared instantaneously across cosmic distances. The very concept of physical reality might give way to something more fluid and malleable, where the distinction between actual and possible becomes meaningless. Yet for all their exotic properties, wormholes also remind us of something beautifully human about the scientific enterprise. The equations that predict cosmic shortcuts were written by minds that evolved to navigate a world of solid objects and linear time. The mathematics that describes folded space-time was developed by beings whose ancestors swung through trees and huddled around fires. There's something almost magical about the fact that consciousness arising from the complex arrangement of atoms and molecules can discover truths about the deepest structures of space and time. This suggests that mind and cosmos are connected in ways that go beyond mere observation. Perhaps consciousness is not an accident that emerged from blind physical processes, but rather an inevitable feature of a universe that is fundamentally mathematical in nature. Perhaps the universe requires conscious observers to actualize its potential, to collapse infinite possibilities into definite realities through the act of measurement and understanding. The story of wormholes is ultimately a story about the power of imagination guided by rigorous mathematics. What began as science fiction speculation has become serious theoretical physics. What seemed impossible has revealed itself to be merely extraordinarily difficult. The boundary between dream and reality continues to shift as our understanding of the universe grows more sophisticated and more strange. Whether or not we ever discover natural wormholes or develop the technology to create artificial ones, the very possibility of cosmic shortcuts tells us something profound about the nature of existence. Reality is far more flexible, far more interconnected, and far more amenable to conscious transformation than our everyday experience suggests. The universe revealed by modern physics is not a cold, mechanical clockwork, but something closer to an infinite ocean of possibility waiting to be explored by minds capable of dreaming impossible dreams, and then discovering ways to make them real. In the end, wormholes represent more than just exotic physics. They embody humanity's deepest aspirations to transcend the apparent limitations of physical existence. They remind us that the universe is stranger, and more wonderful than we can imagine, and that consciousness itself might be the key to unlocking realities that exist beyond the boundaries of space and time. As we continue to probe the mysteries of quantum mechanics, relativity, and the nature of space-time, we may discover that the most profound journeys are not through folded space, but through the infinite landscape of understanding that connects mind to cosmos, in ways we are only beginning to comprehend. As we reach the end of our cosmic journey through the mathematics and mysteries of wormholes, I find myself marveling at how far we've traveled together, not through space, but through possibility. We began with science fiction dreams, and ended up contemplating the deepest structures of reality, the nature of consciousness, and humanity's place in a universe far stranger and more connected than we ever imagined. The story of Wormholes is really the story of human curiosity, reaching beyond the limits of what once seemed possible. From the early dreamers of cosmic shortcuts, to Einstein and Rosen uncovering bridges in the fabric of space-time, from there to today's physicists exploring quantum entanglement, we've witnessed the beautiful transformation of imagination into serious scientific inquiry. What strikes me most is how wormholes challenge our sense of what is real. The universe, as revealed by our best physics, is not a fixed backdrop but a dynamic structure, one that can be bent, folded, and perhaps even shaped by intelligence. Space and time, which feel so constant in our daily lives, are in fact expressions of something deeper, more fluid, and more astonishing. Whether we someday find natural wormholes hidden in the cosmos, or build them ourselves, the act of imagining them has already changed us. It teaches us to think beyond light years and lifetimes, to envision consciousness not as isolated, but as something that might one day reach across the stars. Before you drift off to sleep, perhaps take a moment to look up, if only through a window, and find a star. That light traveled for centuries to reach your eyes. You are not just observing the past, you are participating in it, connected by photons, by time, and maybe, in ways we don't yet understand, by the deeper threads of reality itself. Somewhere in the mathematics of our universe, the equations whisper about tunnels through space, bridges across time, and futures not yet born. Whether these shortcuts exist now or await discovery, they remind us that the cosmos holds more than we ever dared to hope. Thank you for joining me on this journey through the architecture of wormholes. Share in the comments which part of wormhole physics lit up your imagination. Are you drawn to the elegant math of Einstein-Rosen bridges, fascinated by quantum threads that might shape reality, or simply wondering what it would feel like to walk through folded space? The universe holds bridges between every point and every other, but the most profound journey is the one we take together through understanding. Until our next cosmic voyage,